Good morning, everyone. My name's Chris Mullins. I'm with Powermetrix. I'm the product manager here at Powermetrix, and just wanted to welcome everybody to part 3 of our PMX meter school. And this one is talking about CT, PT theory and testing. And so should be a good one. Some of you may have sat in one of our other classes we had that was on CT analysis, basically interpreting data, which is a great presentation put on by Martin Hyatt. So this is kind of, I think of this one as going to be kind of like the preface to that, whereas the one that Martin did was more directed towards analyzing the data after we've looked at the CTs. So I apologize to everybody out there that John Jones is not with us today. So you're just with me. Actually, John is out working with a customer and delivering some test benches that a customer just bought. So that's going out today, which is pretty cool. So again, today what we're talking about is going intro to CTs and PTs, and then we're wrapping up this session for site testing or justification for site testing on Thursday. Should be a good class as well. All right, so what we're covering today, we're going to go over the basics of a CT and PT, and we're focusing mostly on the CTs. I'll cover a bit of the PTs, but the vast majority of this presentation is talking about current transformers. We're going to talk about the accuracy class, burden class, and rating factor of the CTs as well. How to reduce errors, or how to know what's going on, and then some methods of testing CTs in the field. We'll talk about that as well. So a transformer, it really is a device that kind of changes the amount of electricity, usually a voltage or a current, down to a safe application. So as the primary current or primary voltage comes in, a magnetic field is used to step that current down. And a good thing about a transformer is a great form of isolation between the primary and secondary to allow safe operation for the technician. Obviously, the reason why they came up with these transformers, the instrument transformers, at least for the metering type, is that you don't want $1 million piece of equipment that goes on every single service. So they had to come up with a method to be able to step this current and voltage down where the equipment wasn't so darn expensive. And so that's kind of the reason why they had to come up with this. You don't want a substation at every single McDonald's, right? So so you're basically taking the high voltage or a high current and dropping it down to a metering component. So if you look at the graph here, or picture here, you can see where the CTs and PTs are actually mounted on two different bases. For an industrial commercial site, typically they're mounted on the same place. If it's a pad mount, you'll see PTs and CTs mounted into the same pad, and a lot of times nowadays you don't see PTs at all. Which is kind of the reason why I'm not talking too much about PTs. They're mostly used in a primary or substation application. But yeah, the two types of transformers we're dealing with on the metering side is going to be a CT or a current transformer or a PT, potential transformers. Sometimes people call a potential or a voltage transformer a VT as well. So when I say PT or VT, we're talking about the same thing. There is no difference, just how you call it. So PTs, they step down the high voltage down to a lower voltage. Typically at the meter base, it's going to be 120 volts phase to neutral, and some substation applications are 69 volts phase to neutral. They can come in all kinds of different shapes and sizes. Sometimes you'll find a CT-PT combo as well, not just a PT. They're pretty simple. As the output equals the input times the secondary turns over the primary turns. So it's a pretty easy component. That's not really too complicated. They do come in power ratings in VA. We'll talk about that a little bit here in a second. And the typical accuracy classes they have for PTs are 0.3% at its full rating. So, so the typical accuracy classes, like I said, are 0.3 based on cost and budget. They do have 0.6% and 1.2%. And the burden expression is a little bit odd. They actually express it in letters, but the value that is always displayed is power, or VA. So, for example, a common one is a W, which is a 12.5 VA. That would be a common PT you would use for low voltage application, maybe a light commercial industrial application. If you look at the graph on the right, that's what we call a parallelogram. It's an IEEE standard. Both PTs and CTs use a parallelogram. They just shift the angle a little bit differently. But if you look on the x-axis, that is phase angle. So that's in minutes. In metering, we typically use that as, we usually call that phase angle, but using a parallelogram, they plot it in minutes. But it's essentially the same thing. And then on the y-axis, that is your error. So as I go from 0 up to the next level, that is my 0.3%. So notice this red box here, that is my 0.3%, I'm sorry, 0.3% accuracy class. So as long as my plots are staying here, I move within my 0.3%. The blue plot here is my 0.6. As I increase in burden and as my phase error increases, I will make sure that I stay within this blue triangle. And again, if you were with us when we were doing about CT PT analysis, we went over this in extreme detail in the presentation that Martin gave. Good presentation. So the typical low voltage, which is the 600 volt type PTs, you're going to run across a 2-to-1 or possibly a 4-to-1. So for this 2-to-1, what it's saying here is 240 volts phase to neutral or 416 volts phase to phase. So we transform that to 2-to-1. So if it's 240 volts on the primary, we step that down to 120 volts. So basically you're just dividing that by 2. So 240 divided by 2 equals 120 to get to the meter. The same applies for all the low voltage. Now for some of your primary sites or maybe some of your substations, you're going to deal with this medium voltage or high voltage PTs here as well. Same concept, you've got a phase-to-phase voltage here and a phase-to-neutral voltage rating, and it just steps it down. All it is a divider. It's 60-to-1. CTs a little bit differently. They rate theirs to 5, but PTs are always referenced down to 1. So pretty easy to look at, but a nice little handy chart you've got here to look at if need be. So we're going to move on to CTs, which is the majority of where we do our testing and where possibly the errors run across. PTs you can easily test those. It's not the problem, but usually you can find a problem there at the secondary, at the meter, because it's kind of analog, right? So if it's the PT goes out, typically you're going to see it on the secondary side as well, so it's easier to detect. CT is a totally different story. That's why we do a lot of our analysis on the CTs as opposed to much of the PTs. But on CTs or current transformers, these do the same thing. They step down higher current down to lower currents to make it safe operation for the meter technician. The pictures here, for example, on the very top, these are what we call window or donut type CTs. The primary goes through the inside of the CT and uses that magnetic field to decrease the current coming in. Over here on the bottom left, that's what we call a bar type CT. So it's a window type CT with a metal bar going through it that I've seen in some of these compact pad mount style installations where they're stepping the current down. Well, same concept, it's just a different style of CT. And on the far right here, those are your CT PT combos that you're typically going to run across in a substation. And one thing to remember is that they are extremely dangerous. They can kill you. kind of an explanation on the CTs. We went over this a little bit in the first session for intro to metering components, but these CTs here, so if you look at the very top of the CT, that's called an X1 and X2. That is your secondary output. So as the primary current comes through the window of this CT, the step down, so this, for example, I'll talk about this ratio here. So if the CT has a ratio of 200 to 5, what that means is that I've got 200 amps flowing through this CT and I'm putting out 5 amps on the secondary. And that's what that X1, X2 is. X1 is a current coming in, X2 is a returning current back to the meter. And then when you're operating or when you're doing maintenance on the CT, you insert this shorting bar to shunt the currents there to the meter. And we'll talk about that in a second as well. Other parts of the nameplate, obviously there's always a serial number. The voltage rating, this is the standard voltage, 0.6 kV or 600 volts. So this CT is what they call a low voltage, which is anything below 600 volts. Anything above that would blow the transformer. Rate factor or rating factor, I'll talk about that in detail and later on. This is the 4 rating factor. It comes down to 1, 2, 3, or 4. Those are the 4 different rating factors you have. And then lastly, they always stamp the ratio of the CT here, so it makes it more obvious. If you were in my Guess the Metering Error class, you know that is not 100% true. We have seen it in some cases where the nameplate stamped on the CT does not meet the nameplate on the CT itself. And that becomes a problem when they insert that into the site. And the only way to detect that is when you do an actual ratio test. And we'll talk about that in a second as well. So very similar to the PT parallelogram, this is a CT parallelogram. Same concept. In that red window is our 0.3% tolerance. So when the CT is manufactured, they put it on a sinusoidal waveform, stable load coming into the CT, and they check to see how well the accuracy is at certain steps within its range. And again, I'll talk about that in a second. But each CT has its own accuracy class. Typically, they're all 0.3. And that's where but it's also that also 0.3% is dependent on a lot of different factors. So 0.3% is only good when the CT is at its full rated load. Now that doesn't necessarily apply to extended range CTs, and I'll get into that. But a typical non-extended range CT, at full rated load, so for example, if you have a 200 to 5 CT, the manufacturer guarantees that CT is within 0.3% accuracy at 200 amps, I should say. Once you get at 199 amps, 1 amp below, now you're within that 0.6% range. So you drop as soon as you get below that full rated load. And you can go all the way down to 10 amps, which is like 20 amps, for example, on a 205 CT. You're guaranteed 0.6% down to 20 amps on a 205 CT. That's what that means when it talks about 0.3 and 0.6. What's the difference? And so all of that, and not to mention that's just amplitude error. When you talk about phase angle error as well, which is this x-axis here, that's when you start getting at your total amplitude and phase error, which is the total error of the CT. This is a bathtub curve we use quite a bit in our presentations, but I'll try to explain this. We're looking at a CT that has a 0.3% accuracy class at a burden 1.8. So it maintains its accuracy up to burden 1.8. So if you look here on this axis, this is 100% rated load. So you can notice that it's within its 0.3% accuracy right there at 100% rated load. And so this has a rating factor of 4, so it can go all the way out to 4 times its rating. So it's still holding its 0.3%, right? But as soon as it exceeds that, it goes into saturation mode and the accuracy goes way out of tolerance. So you've got to keep it within 4 times its rating. However, if you look at this same CT and you drop, notice that my error increases, gets worse as I go all the way down to 10%. And once I get past 10%, there is no spec for a non-extended range CT. That's what this chart is trying to tell you. Great chart, but it shows the different resistances, as you can see how it kind of transfers as my, what I'm trying to say is a burden and accuracy are very much dependent on each other. This is another way to look at a 0.3% accuracy CT. Again, this is a rating factor of 4, so we can go 4 times its class. But notice how when it gets down to 10%, it drops down to 0.6%. There is a higher accuracy CT, which is what we call a 0.5, accuracy 0.5, and it can still hold its range up to 4 times within 0.5, but then when it steps down to 10%, then the accuracy the error doubles to 0.3%. So it's still within a good range. A little bit higher cost CT, but it's out there. And then the most accurate CT you can get out there is what we call a 0.15S, and so it stays within all the way down to 5% of its range within 0.5% accuracy. Now, I want to be clear that when we talk about these accuracy, these are under ideal conditions. So this is under a lab condition, and it's assumed at 30 degrees C, which is around 86 degrees Fahrenheit. That was where it holds its temperature or holds its accuracy. So as burden increases and as temperature increases, which is a very common phenomenon we have in the field, this accuracy is not guaranteed anymore, or it derates. Also, when we get to the point where we're actually testing the transformer, we're using a probe, let's say like a flexible current probe, or using a sensor link probe that will decrease the accuracy as well, because a probe is meant for versatility, but you have to have the trade-off on inaccuracy when you have to position the probe to get into the cabinet or around the conductor to get a measurement. So your accuracy goes down a little bit as well. So what I'm trying to say is I can get a 0.15 SCT in the field, but it doesn't necessarily mean it's going to translate to 0.15% across the entire range and it's actually in the field. So I just want to be clear on that point. So a typical service we have there, you can see each one of these stars here is an actual termination of a connection from a wire to a switch. So this is going to the meter. So here's my CT. I'm going to a test switch. I've got two connections here between the secondary and the primary. And then here's my test switch going back, and then another again to the meter. So I've got all these connection points coming to it from the meter, both in the CT and PT. Each one of those stars represents an additional burden point. And so we'll talk about, the problem that burden can have, or resistance, because, as you add more resistance to the circuit, you get less secondary current to the meter, which therefore means you're not billing as much as I should. So again, burden can reduce CT accuracy because you're getting less secondary current to the meter. Wiring, for example, if the wire is not torqued down properly, or if there is any kind of corrosion. Let's say you're in an environment near the coast. Corrosion is a real big problem because that can cause more resistance there in the wiring. Also, people also forget about the actual wiring gauge. So they'll use a smaller gauge wire, whatever they had off the truck, run that wire, and that can be a problem as well, and we'll talk about that. Also a shunt bar. Sometimes when the new installation is put in, the shunt bar is sometimes left, and the problem is that you would think that when you leave the shunt bar in, that means zero current flowing to the meter, and that's not true. So if the installer is there leaves a shunt bar installed in the CT, the meter keeps on turning. And so it's not really triggering to the installer that, oh, well, there's something going wrong because the meter's actually turning itself. It just means a lot less current, between 50 and 80% of what should be there when that shunt bar is installed. When you get a CT from the manufacturer, they usually supply, kind of a accuracy and burden. So on this particular CT, it's showing here the meter accuracy. So this B 0.1 means with 0.1 ohms and 0.2 ohms and 0.5 ohms. Here is the accuracy range guaranteed based on the amps that's in this CT. So for example, this CT at 1,000 amps, it's guaranteed 0.3% class all the way, 0.3% error within, it's all the way up to 0.5 ohms. But once you get down to 300 amps, you're dropping down, remember, below that 100% range, and so you're guaranteed with 0.6. And it gets even worse as your primary amps go down. So CTs, and if there's one thing you walk away from this presentation, that CTs like to be overdriven. If you oversize a CT and you put very little current through there, the CT is just not as accurate. So most CTs out there are they're rated at 0.3 burden, but sometimes there's CTs out there that actually have a 0.1 or a 0.2 ohm burden rating. So if you have a maximum burden rating of a 0.1 ohm, there are times that just the wiring gauge alone will put you over the burden rating of the CT itself. So for example, if I've got 50 foot of number 12 wire, I've already exceeded my or at my 0.1 ohm burden max. So do not forget about the importance of the gauge wire and the length that you have running between that CT and the meter. A lot of customers, need, they call up and they say they need these extended, extensions for their Powermaster to get to the meter to the CT, and I always ask them, man, I hope you guys have a pretty heavy gauge wire coming from the CT to the meter, because it does take into account, because there is going to be a loss when you run 100, 200 feet, depending on what the wire gauge is. So keep that in mind. As I mentioned about the shunt bar, if the shunt bar is left installed, it will make a difference. And the problem is that people think that, again, when the shunt bar is installed, they think, okay, the meter's not turning, it's not getting current. That's not true. It actually is getting a little bit of current, and it will throw off your ratio error whenever you run it. Polarity is extremely important as well. Dot to the pot, that's a pretty common term we use in the metering industry. So that is the polarity. So you want to run your polarity to the dot. Otherwise, you're getting opposite polarity, and that can mean wrong metering. Let's talk about rating factor. On a CT nameplate, you're going to see what they may call it an RF. That stands for rating factor. Usually it's a 4. That's most of the ones I've seen nowadays. So if a CT has a rating factor of 4, it means up to 30 degrees C or 86 degrees Fahrenheit. It can be used up to 4 times its label. So if it is a 205 CT, you can drive that CT up to 800 amps and still hold its accuracy class. That 0.3% accuracy class, which is where we want it to be. So always try to overdrive your CT. However, and I will put this as a however, temperature can affect this. So think about a July day down in Florida in a pad mount. So I'm guaranteed my accuracy at 4 times at 30 degrees C. But as my temperature rises, notice that my accuracy decreases as well. So a CT with a rating factor of 4 at 30 degrees C, you derate your rating factor once your accuracy once your temperature increases. So if you get, for example, 55C is around, I think it's around 130 degrees Fahrenheit. Notice that now you're dropping down to this 3 times rate. So you're not able to drive that 205 anymore. You can't drive it 800 amps anymore. Now you can only drive it at 600 amps. So when you are sizing your CTs for these installs, make sure you take note of the temperature that is going to be in. If it's an outside temperature mounted on a pole, you're more likely to be able to handle that that temperature range. However, if it's in a pad mount, you could have a little bit more problem because that heat retains in that pad mount cabinet. So now let's start talking about ways we can actually do a ratio test. So we've kind of talked about the components, what to look for. We're looking for the rating factor. We're looking for the nameplate. We know where the accuracy ranges between the burden and then the temperature going on. So to be able to verify that CT is performing, we want to talk about the actual ratio test, which is the most accurate way we can do it. So what you're doing is you're measuring the primary, usually with a different type of probe, usually like a flexible current probe or maybe a high voltage probe like the centraling probe. You're actually mounting to the primary of the CT and then using a different probe at the meter itself. Usually we use a duckbill, which is a black and white probe you insert into the test switch to get the secondary current measurement. So you're looking at the ratio. So again, think about it, if I have a 205 CT and I'm measuring 200 amps on the primary, I should expect 5 amps on the secondary, right? That's what the ratio test is. You're just measuring what the primary is versus what's coming out on the secondary to make sure that that CT is performing well. Some alternate approaches. So for example, you're not able to actually access the CT, or it's too dangerous to access the CT. You can do a burden only test. It is limited. Only thing you're doing with a burden test is you're just validating that the CT can handle a little bit additional resistance. So it kind of just, so say for example, and what a burden tester is just really a bank of resistors that you're adding in sequence to kind of ramp up the CT and see how well it performs. Theoretically, as we add more burden or resistance, you're going to have less secondary current coming out of the transformer, which is very true. So you're looking for almost like a downward slope or a downward trend as I add additional burden. That's all it's really telling you. So it's not really telling you what the ratio is, it's just telling you that the CT can handle additional resistance. Another method is admittance testing, which is good to use, if you have a light load conditions. But again, it doesn't give you ratio results, and it's not very accurate either. The problem I have with admittance testing is that you need a baseline. So and I'll kind of explain what admittance testing is. You're actually putting it's an audio frequency into the secondary, and so you're looking for, it's around like 1500 hertz. It puts into the transformer. You're looking for a response back, and so that's kind of the reason why it may be a good method if you have a light load condition. But the problem I always have with it is you have to have a baseline. So how the heck do you have a baseline if you have a new installation? So if I got a brand new installation, I've never tested the CTs before, I go out there, I do a admittance test, and it gives me a value. Is that good or bad? I don't know. I'll go back out a year later, it gives me the same value, so forth. But it never really told me, was it good to begin with? That's kind of my problem I have with admittance testing. Otherwise, again, it's still not going to compare to actually doing a ratio test. So like I mentioned with the ratio test, you're actually verifying that everything coming out of the primary, all the way that flows through all that wire to the meter, is coming back with into the right ratio. So that's what we're doing when we're doing a ratio test. Oops, sorry. So here are some examples of what the customer's doing. In this case, on the top left is what we call a pad mount installation. This user is actually using a flexible current probe to wrap around all of the conductors flowing through that transformer, and we do need to measure all of the current flowing through those conductors as well. On the bottom left, the technician is using what we call a high voltage probe, which is the bottom left and the right. So it's using a high voltage probe, which is great for installations that are over 600 volts. Actually required for anything above 600 volts. So we have a probe that can actually go around those conductors and get the ratio that you need to get. So at the secondary, this is a test switch, and so those white and black probes, what we call duckbills, those are inserted into the test switch. So you're getting that secondary output of that transformer as I'm measuring it from the primary side. And so I'm just validating that the ratio coming out is coming out correct. So if everything is perfect, everything's well, you're going to get really, really good results. In this case, if this was a 250 to 5 CT, we use some what we call the SR752 clamp-on probes, which are very, very accurate around the primary, and then measured the secondary there at the test switch. So this is a perfect example. No ratio error, no phase shift, but it looks good. And if you look at the parallelogram, everything was within that small window, right? No change in the secondary current, no change in the primary current. Now, are you ever going to see this in the field? Heck no. This is only something we simulated in the lab. Now let's talk about what you may see in the field. Oh, again, when the Powermaster, you're actually seeing the change of secondary amps here, which is virtually 0. Ratio remains the same, and the error remains the same as well. So these are just really, these 3 slides here are representing the same information, just different points of view. So this is just a simple point of view, a graphical point of view, and this is the detailed version of that graphical representation. That's all it is. So 3 different points of view using the same data. But now we get into a little bit more real life situation. This CT was a 5 to 5, but it had a 0.1 ohm max rating on it. So you can tell that it doesn't perform very well. The Powermaster will give you a fail message once it exceeds these ratio errors. And these ratio errors can be set up based on the customer's point of view. In our area, we're governed by TVA, which is Tennessee Valley Authority, and they give the utility 2% plus or minus total error. And so our customers around this area set up their Powermaster to be within plus or minus 2%. So if it fails outside that number, this number goes red. In this case, I think this one was set up as a 1% error. So that's why these things pop up and fail. But we're at least validating that the ratio is coming out right, or as expected, I should say. So again, notice how ratio error gets worse. Secondary current drops off quite a bit on each phase, especially after I exceed that 0.1. Notice I go, here's my first burn step, 0.1 ohm, and notice how much it drops off after that, right? Pretty significant. Same thing is shown here on the parallelogram. Okay, at 0.1, and then it just kind of goes off the chart for that 0.1 ohm CT. If it's not clear, I don't recommend 0.1 ohm CTs. Get at least 0.5. This one also, sometimes all customers ask me about harmonic effects, and you know, when we do a meter test and I look at the harmonics, I don't really see it really translate to the meter error, but I definitely see it translate to the CT error, because CTs aren't as designed as well to be able to handle the harmonics like a meter can. So if you look at the chart on the left, the parallelogram on the left, you'll see that B phase, which is that yellow phase, you can see how bad harmonics can affect that measurement. The error is way off compared to what's going on with the other two phases. However, if we remove that harmonic load, so it's 100% purely sinusoidal waveform, the accuracy comes within tolerance. It's not perfect, but it's much, much better than it was with the harmonic removed. Same as that CT, is just how well that CT performs under harmonic conditions. You can also see what's going on. So I had about the harmonic load on there. You can see how bad it kind of disrupts the waveform here. This was actually a switching power supply we had on the CT, and it had about a 50% harmonic distortion there on B phase. So you can see how well easily it is to see when that thing fails. And it passed. So we take out the harmonic load, and it passes like with flying colors. So when we do a ratio test, guys always ask me, I was like, well, is it good or is it bad? So let's say I've got 105 CT and I measure 99.68. What does that really mean? So in this test, we measured about 35 amps on the primary, which translated down to about close to 1.8 amps. So if you take the ratio and you step that down to 5, remember we're down to 5. So to kind of calculate that, you take that primary amps or 35 amps, divide that by the secondary, which is 1.8 or 1.8 amps, and then you multiply that product by 5, then you get that 99.68. That's how you calculate that in a very manual way. So let's say if it had been 100 to 5, and so we took those same primary amps and measured 1.7 amps. So what we're saying is that we measured 1.799 more than what we should have. So if we tested the ratio 99.68, it means that we are measuring more current than we should. This error is in the utility's favor. In the opposite direction, let's say it's 105 CT and I'm measuring 101.6 something, that is in the customer's favor, if that makes sense. So what that means, when I say it's in whose favor, that means that if it's 99.68, that means the utility is overbilling the customer in a way. In the opposite direction, the customer is getting a deal, getting a bargain on their power. So that's how to translate that when you try to or interpret that value in a very simple method of who wins in this case. So is it the utility who wins or is it the customer that wins? In this case, the utility is winning. So you can kind of see how as we add additional burdens, so each one of these tables, 0, 0.1, 0.3, you can see how the ratio changes, and that translates to the percent error here as well. So it goes from 0.07 all the way to 0.05 to 1.4 as we add additional burden. And that's where it starts to swing in their favor, right? So it's not so bad here, but then it starts to get a little bit worse, right? Okay. If we just do strictly a burden test, this is a 0.2 ohm CT. It's actually within, it doesn't look that great. You know, this value here, I'm stepping it down, I'm decreasing my current, but it's actually within specs. But if I had the same CT with a different burden rating, now it looks a little bit different, right? You get the same performance, same drop, but the burden rating shows that it's out of specification, just strictly on a burden-only test. And again, a burden-only test just tells you one thing. It doesn't necessarily translate to that there's a problem, which is kind of what the next slide is. It's, a burden-only test that is good probably means that the CT is good. But let's say you had a bad burden test. That doesn't necessarily mean anything. I do some consulting work for another utility, and one of the gentlemen, he'll send me data, and he's curious as to what's going on with this test. I see the burden drop way off, and then it goes back up and it goes back down. So what he's seeing is he'll see a drop and then it go back up and do this kind of seesaw thing. So he thinks there may be a bad CT, and it's not. So 9 times out of 10, when you see kind of a seesaw burden plot, burden plot like this, kind of a sawtooth, maybe not seesaw, but sawtooth, that's probably going to be a load change. So something happened during that CT burden test that caused the load to change, and therefore it kind of made that kind of weird looking plot. So doesn't mean to swap out the CT. It just means try to go back, do another burden test, when the load is a little more stable. If it's never stable, let's say it's like a wood chip mill, you may want to go back when it's kind of idling, and that may give you a good idea how that CT is performing. So here's an example. So I've got this. I did a CT test. CTA, I got a pretty big error here, 12% error. But B and C look good. So that's kind of strange, right? But look at my parallelogram and notice again my ratio error is trailing way off, a drop off from secondary current, but parallelogram is way out there. B and C are still maintaining their accuracy, but A phase is just weird. Looking at my vector diagram, can't really tell much what's going on. It does look like I got a little bit more current here on A, but nothing that's really sticking out. What happened here? So this is it's a good time right now, as COVID-19 has kind of put a strain on our economy. This may pop up more often than we expect it to be. Actually, this exact example happened around 2008 when the first big economy tank happened, at least in my lifetime. And then this next one that's coming up with COVID-19 doing the same thing. What happened was that the customer just put some wire through his CT, and what that did, they just added additional turns. So if you add additional turns on the primary, that means you're getting less secondary current at the secondary, right? So your ratio is going to be way off when you do a ratio test, but when the customer does that, the meter is billing less secondary current. So he's actually getting a bargain. Let's just show it here. No. So it drops the current down to the meter and 10-20%. So that automatically translates to how much power he is consuming, and therefore his bill will drop. And so the utility will never be able to discover that until they actually do a ratio test, because that way they can verify that the turn ratio from the primary to the secondary match, and there is no possibility of theft where the actual customer is creating more turns to decrease the amount of secondary current going to the meter. This one's fairly easy to see. So I just looking at my vector diagram, what do we think is going on here? Right? Phase A CT is reversed. So what happened was probably on the secondary, I think on this one. So the primary came in correctly, but when they were wiring up the meter can itself, the secondary side was swapped. So that's why you have a 180 phase reversal. Sometimes the meter will come back with an error on this, sometimes it won't. But obviously if you hook up equipment like a Powermaster, you easily see the phase shift. Similar here as well. Notice that my secondary current for A is lined up with my voltage for B. Same thing for here. What happened where was the A and B swap? So as the technician who was installing the service actually swapped the wrong phase, maybe the color code was wrong on the secondary line coming in, but that's what happened on this case. So that kind of wraps up this presentation. I want to kind of go back real quick because I wanted to talk about extended range CTs. So I forgot to talk about that in the beginning. So let's go back to this chart. So for those who use extended range CTs, and I do really love extended range CTs. I think they're a great product. A couple manufacturers have been coming out with them. Two big reasons why I like them. The number one reason is that they hold its accuracy much better than a typical CT does. So for example, this is a very standard 0.3% accuracy class, and extended range CTs can come in different accuracies. They can go 0.3, 0.6, 1.5, or 0.15. But what makes them so fascinating is that they can, so with this 0.3% accuracy class, once I get below 100%, now I'm down to 0.6. But with the extended range CT, I can go all the way down to here, 40%, and still hold my 0.3% accuracy. Awesome. I love it. Now, and then you can also go all the way down to 4% to hold its 0.6%. So it shifts this plot all the way back down here and holds its accuracy all the way down, which is awesome. Number two reason why I love extended range CT so much is that it helps with stocking. So I've seen these extended range CTs, there are 200 to 5 CTs or 500 to 5 CTs. So all I gotta do is I can carry one particular CT and then use these for all my installations, because I can use that rating factor, right? So I can use a 400, a rating factor of 4, get 4 times of whatever that is. So if I've got a 505 CT, I can get up to 2,000 amps. 2,000 amps, all the way up. So for 205, I can get 800 amps. So great product, great for stocking. Oh, and one other thing too, it helps with your billing multiplier, guys. If you have so many CTs out there, you have 105 or 205 or 505 there in stock, you always got to keep in mind once you're doing these installations, what's my billing multiplier? Because I've got to divide it down. So if those who don't know what a billing multiplier is, it's the value we use for the billing side, because we want to transfer everything down to 1. If you remember, I talked about the PTs, they have a value to 1, but the CTs, you've got to step it down. So a 200 to 5 translates to 40 to 1. So I take that value of 40, multiply it times my PT, if I have a PT, and then I get a billing multiplier. Let's say I have a full inventory of these 200 to 5 extended range CTs or 505 extended range CTs. I only have to worry about one billing multiplier, unless the rare case I have a different PT that I may be installed. So again, great for accuracy, because you can use them all the way up to a rating factor, all the way down to 4% of its rating factor and hold within 0.6, which is awesome. And then you can also, helps with stocking, and also it will help you with your billing multiplier. You're not having to keep up with so many multipliers. You'll just have basically one to keep up with. So that's what I want to talk about with the extended range CTs, because I really, really like them. I think they're a great product, and I highly recommend anyone putting in new installations to seriously look at extended range CTs. I just think they're great. All right, so wrapping this up, Thursday, stick around. That's our final seminar on this PMX meter school. We're going to go over the justification for site testing, so stick around for that. It's been great, but we will see you Thursday.